For me it's a real pleasure. And good morning, or good afternoon, buongiorno. I have some introduction about what is my region. Italy, you know Italy because of the shape, and in particular I come from this island. This island is named Sardinia, and in particular from this little spot here, Sassari. Sassari has in common with you that we were invaded by the Spanish. Spanish spent about 7 centuries in Sardinia. So you can see the architecture of the cathedral of Sassari is typically Spanish. This is our main square, Piazza Italia. And Sardinia is well known in Italy, in Europe, because of the touristic attractions, because we have very nice beaches, playas, you say. Yes. So I invite you to Sardinia if you have time to spend. Okay, and this is my department. It's not so big as yours. We have, Sassari has only 120,000 inhabitants. So for you is a village. So in my department there are only about 35 people, 35 researchers, professor researchers. Okay, what I'm going to tell you today, I would like to tell you something about 2 different alternative approaches to polymer materials, as in the title. And the first is an alternative method of polymerization, alternative technique of polymerization, which is a frontal polymerization technique. And the second is an alternative method to obtaining graphene-based polymer nanocomposites. These 2 methods are linked together. I will show you how they are linked. Okay, first of all, let's talk about frontal polymerization. If we take into consideration the main classes of reactions having practical interest, we discover that they can be classified in 2 main categories. The first is the category in which I put the reactions occurring in heater reactors or molds, and the reactions occurring by simple mixing the reactants, and in which the reaction occur at low temperature or at room temperature. So what I mean? I mean that these reactions need energy supply from the beginning to the end. We have to heat them, if for the first of the 2 subcategories, or they have the energy from the environment, but from the beginning to the end. In the second category, I put the reactions occurring spontaneously, but only after ignition. For example, we have systems that are inert, but if we ignite them, they react spontaneously, and they don't need to be supplied with energy, but we just need to ignite them in order the reaction to occur. In this category, I put, for example, explosions, combustion, and frontal polymerization. If I want to give you a sort of official definition of frontal polymerization, I can say that frontal polymerization is, I read, a mode of converting monomer into polymer via a localized reaction zone that propagates through the coupling of thermal diffusion and temperature-dependent reaction rates. Well, it's not a very clear definition. We don't know what frontal polymerization is. And so I think it's better to show you a movie. Before starting it, I would like to tell you what are you seeing here. This is a soldering iron, which is now heating in this localized zone. This is a normal, very common test tube with some monomeric mixture inside. And this is a thermocouple with its junction placed more or less here. The thermocouple junction reads the temperature, and this is temperature red. You can see here we have the formation of a front, a polymerization front. This is liquid, this is already solid, this is a polymer. And if you consider that these notches are placed at 1 centimeter one from the other, you can have also an idea of the velocity of the fronts. You can see that the temperature is now increasing slowly, but it's increasing only because the system is heating. We don't have a reaction now, but we have the reaction. So the thermocouple junction records the reaction when the front approaches the junction itself. And you can see how high is this temperature, or might be this temperature. We don't need to supply any energy apart from the initial ignition. And in this case, the system reaches more than 200 degrees. I don't remember how much now, we discover it in a moment. And then I stop it. Okay, 270 degrees more or less, without heating it, apart from the ignition. This is the polymer, and believe me, the conversion of the polymer in these few seconds, few minutes, is almost complete or complete. So it's very easy and very fast. Now, if we take the temperature, if you record the temperature as a function of time, we have this temperature profile, which is what the junction red. And you can see we have the first zone, which is horizontal. It means that frontal polymerization is pure. Means that it's the only phenomenon occurring in our reactor in that at a given time. Then we have an increase of temperature, and then we have the system in which cools. If we measure the position of the front as a function of time, we discover that front velocity move at front velocity are constant. Fronts move at a constant velocity. Let's go a little in depth. Just analyze the data. If we consider an ideal system is a system in which we have only, which is adiabatic, we don't have any heat diffusion, and we have only frontal polymerization as the only phenomenon occurring. We should observe that the first part of the curve is horizontal, which is the initial temperature. When the thermocouple arrives and crosses, or the front crosses the thermocouple junction, we have a sudden sharp increase of temperature up to the adiabatic temperature, and then the temperature is kept. This is ideal, obviously. In practice, we have that after reaching the maximum temperature, we have that the system cools, obviously. And also the increase of temperature is not so sharp, because before reacting we have the system that is the the junction reaps the heating, but not reaction. And I can call this system, this frontal polymerization pure, but if I observe that I have an increase of temperature like this, I cannot call my frontal polymerization pure, because this temperature increase before the front reaches the thermocouple junction means that something else is happening. Something else generally is polymerization which is occurring simultaneously. So we have two phenomena at the same time. And this is generally what we don't want. Analogous consideration can be done by considering the front position, because as I told you, a pure frontal polymerization is characterized by constant velocities, but sometimes we can observe that velocity is not constant. And again, it means that something else is occurring. So our frontal polymerization is not pure. Okay, after this introduction, I just tell you something about a couple of systems. We have studied a lot of systems these years, obviously, and these are the main families: polyurethanes, polyacrylates, polydicyclobenzene, interpenetrating polymer networks, nanocomposites, hydrogen, initiators which work well for frontal polymerization. We try to apply frontal polymerization to the consolidation of porous materials, stone, wood, paper, and so on. And now, due to an idea of Ernesto Rivera, his idea, we started something about nonlinear optics. So, I will tell you something about nanocomposite, graphene-based, and hydrogen. Hydrogens first. Hydrogens, what are hydrogens? As you know, hydrogens are cross-linked materials which are able to swell in water. They find application in many fields. Generally, they are biomedical fields: tissues, cartilages, and in particular drug delivery systems. These are most important, probably, or one of the most important. And among the hydrogens, I am particularly interested in those which are also stimuli responsive. What is a stimuli responsive material? What is a stimuli responsive hydrogen? It's a hydrogen which changes its volume in response to an external stimulus, in response to an external environmental changement. For example, we can change temperature or pH, or we can apply an electrical magnetic field, or we change the ionic force, or other. And we have that this swollen gel swells and increases its volume. And we apply an opposite stimulus, we have that the swollen gel swells. Among the stimuli-responsive hydrogens, I am particularly interested in those which are thermoresponsive. That means that temperature is the trigger. And thermoresponsive hydrogen, as you know, are characterized by a critical solution temperature, which can be a lower critical solution temperature. That is a temperature below which the hydrogen is swollen, or a HCST, a higher critical solution temperature, which is the temperature above which the hydrogen is swollen. Generally, LCST is the most common. In particular, the most studied hydrogen is poly and propylacrylamide or polynipam. I call it polynipam now. Very much simpler. Which is the most extensively studied thermal responsive polymer, and which exhibit a lower critical solution temperature at about 32-33 degrees centigrade. It's very interesting for its biomedical application, in particular for the control release application. But it has some problems. One is that the monomer is quite expensive, and the other problem is that the monomer has some biocompatibility problems. We try to copolymerize it by using frontal polymerization with another monomer, vinyl caprolactam, which is biocompatible, which is characterized by the same, or more or less the same, lower critical solution temperature at 32-33 degrees, but which does not have a sharp transition between the swollen and the deswollen states. However, it's cheaper and less cytotoxic than Nipam. Okay, we perform a main synthesis by varying the ratio between the two monomers from, if this is the Nipam molar fraction, from 1 to 0, and by keeping constant the 1-to-1 ratio between the monomers by varying the amount of crosslink. Okay, what we observed is that by increasing the Nipam molar fraction, we have an increase of the maximum temperature reached by the front from 125 to 155 degrees centigrade, more or less, and a corresponding increase in front velocity from 0.30 to 0.75, more or less, centimeter per annum. This was the series A, in which we changed the ratio between the monomers. When we fixed the ratio to 1-to-1 between the monomers, we didn't find any variation of both Tmax and front velocity when we changed the amount of crosslink. These are the values we found. But we are interested in the thermoresponsive behavior, so we measured the swelling properties. The swelling ratio is defined by this formula, MS minus MD on MD. MS, what is MS? MS is the mass of the swollen gel. MD is the mass of the swollen gel. What can we see here? The black trend with triangles are this. Is this sample, which is the samples which does not contain Nipam, and you can see that the transition is not sharp, and also the swelling is not so high. The red and the blue curves are those of the frontally polymerized and classically polymerized samples. Classical polymerized means 80 degrees for 2 hours, 80 degrees of heating. These are those referring to polynipam, the other homopolymer, and you can see the swelling ratio is higher than that of poly and vinyl caprolactam, and the sharp transition at about 28-30 degrees. Okay, but the copolymer with, you can see F2, 75% of Nipam, 25% of vinyl caprolactam, swells even more than what the polynipam does. So we can substitute at least 25% of Nipam with vinyl caprolactam. The system is less cytotoxic, it's cheaper, and the swell is higher. If I compare the samples obtained by the classical polymerization and the frontal polymerization, we don't observe almost any difference in the glass transition temperature, but I remind you that frontal polymerization happened in 5 minutes, and the classical polymerization took about 2 hours. What happened? Okay, this scanning electron microscopy analysis. These samples are both polymerized by frontal polymerization. In this case, we have the homopolymer NIPAM, which is compared with you remember, the samples which swells most. And you can see that this is a typical porous structure of polynipam. We found it every time by using any method. And the situation is quite different if we have a 25% of these other monomer. We have a broader pore site distribution with pores in this case that comes from 0.1 to 1.5 microns instead of pores here that are comprised between 1 and 2 microns. So we have an effect of the monomer. But what is the effect of on this structure? The effect of the polymerization technique. In this case, we have the same system, the one-to-one polymer. This is called polymerized by frontal polymerization, and this is called it's obtained by the blast batch classical technique. In this case, yes, there are some differences, but they are not so important. More or less, we are in the same situation. This is more regular. Nothing special. This is just to tell you, to show you that if we increase the amount of crosslinker, we don't see any pore, but this is quite obvious. Okay. What if we copolymerize NIPAM with another system? For example, by using this salt, SPAC, I call it SPAC. 3-sulfur-propylacrylate potassium salt. Why we use this monomer? Because we would like to increase the swelling ratio. The idea is if we use a salt and I put the salt in water, the compatibility between the salt and water should be higher. And so we try to copolymerize NIPAM with this. But we wanted also to to substitute NIPAM. For example, with another monomer as acrylamide, which is even cheaper. What happens? The first instance, NIPAM with SPAC first. We perform this synthesis in the first 3 are those in which we use this amount of crosslinker. The crosslinker is bis and methylene acrylamide, I don't remember, yes, I think. And this is the ratio, the amount, the concentration of the monomer, of NIPAM. Why from 12 to 37%? Because in that range, frontal polymerization occurred. Because frontal polymerization has some ranges in which occurs. And our job is to find these ranges and possibly to extend these ranges. And we extended the ranges from 0 to 100% by increasing the amount of crosslinker from 1 to 5%. As you can see, the higher the amount of Nipan, the higher the max and front velocity were in all cases. But what about the swelling ratio? Well, what is very interesting, in my opinion, is this curve. It's the sample with 12.5 mol% of Nipan and 1 mol% of crosslinker. We reached this very high value of swelling ratio, 35,000%. While using Nipan alone, we are more or less in this zone. So we have a very high increase of the swelling ratio by using this command. Okay, I can go a little bit faster. Now, let's remove completely Nipan and use a second acrylamide. Well, we copolymerize acrylamide with spark in these ratios, and what I would like to tell you is just that even in this case, also in this case, we found a very high swelling ratio up to 14,000 here. So it's possible to use a monomer which is cheaper than Nipan, and in any case we can have a sharp transition. You can see we have a sharp transition here in the same region of the polynipan, but we have a system which is more absolutely cheaper, because acrylamide is, if we compare the price of acrylamide with the price of Nipan, I discover that acrylamide is really less expensive. Okay. The second system now. Graphene. Nanocomposite in general. We studied many nanocomposites prepared by frontal polymerization. You know that nanocomposite materials are those materials in which we add fillers that are at least one of the 3 dimensions which are in the range of nanometers. Some of them are or have all the dimensions in nanometer ranges, for example, fullerene. Some of them are 2 dimensions in the nanometer ranges, for example, nanotubes, carbon nanotubes, and others have just 1 dimension in the range of nanometers. For example, clays, molybdenite, and graphene. What is graphene? As you know, graphene is any single layer which constitutes graphite. Very simple. It was for the first time isolated by